Hey, my name is Jason Zhang, and this is my Motion of a Falling Object Lab project for Physics 2211 at Georgia Tech. Introduction. The purpose of this lab is to observe the motion of a falling object dropped from rest. We will use the tracker for our observational data and compare it with glow strips computational models with and without the drag force. And here's a preview. In this lab, we found the ball to have a downward, non-constant acceleration which differed from the results of our computational model without drag. After accounting for the effects of drag, we were able to get a more accurate model for our position versus time graph. Some of the fundamental physics principles which will be demonstrated in this lab include Newton's second law, which states that a net force is equal to the product of mass and acceleration, as well as the gravitational force, which is basically just Newton's second law, and it's always pointing in the negative y direction and is equal to the mass times the acceleration due to gravity, which is negative 9.8 meters per second squared. Lastly, we have the drag force whose magnitude is proportional to the square of the object's speed. Some additional formulas which we will use to create our computational models include the position update formula and the velocity update formula, both of which can be derived from Newton's second law. Assumptions. Our system, which is the crumbled paper which weighs 4.5 grams, the surroundings include everything else, my hand, the air, the ground, etc. For our model without drag, we will assume that the only force acting upon our system is the force due to gravity, which is negative mg. In other words, we will ignore the air resistance for now. Here are the initial conditions. Without drag, we have 0 initial velocity, and we're starting at 0, 0.0243, 0 meters. And there's a net force acting upon the ball from the moment the ball is dropped to right before it touches the ground. And this force is constant, and that's just going to be mg. Now, for the initial conditions with drag, it's basically the same, except there's now a non-constant force acting upon our system. This new force can be seen on our free body diagram. This is the video after being analyzed in the tracker. We can see that the velocity time graph is curved, meaning there is a non-constant force acting upon the system. Here are our initial conditions, which we saw earlier, and I changed the delta t to match our frame rate. The proportionality constant for the magnitude of the drag force will be 0 for now, since we are not accounting for drag in our model. We also note that for this model, the only force acting upon our system will be the force due to gravity, so here is the net force within glow script. We will also need the velocity and position update formulas to predict the motion of our ball. Here's the position versus time graph with only the gravitational force. Note that the slope of the predicted graph has a greater rate of change, meaning we are assuming there is no air resistance acting against our direction of motion. And here's the glow script code with drag. The code is similar to the previous model, however, we will now add a value for the proportionality constant of the drag force, and we will include the drag force into the model. Here's the complete graph of our position versus time graph. We see that after accounting for the effects of drag, we were able to get a more accurate model for our position versus time graph. Potential errors. There are a number of potential errors which could have resulted in the differences between the position versus time graphs of our observed data and computational data with drag. Some include the air currents within the room, which could have blowed the ball a little bit in the x direction or even y direction and affected our position versus time model. And also the crumbled paper ball has uneven surfaces, which also could have affected its motion. What does it mean? Our computational model with drag predicts a terminal velocity of negative 4.5 meters per second since this is the graph's horizontal asymptote. Since the ball reaches its terminal velocity when F drag is equal to mg, this means that the net force and velocity is constant after it reaches this point. And we also see that in the free body diagram that mg is equal to the force due to drag when the ball reaches its terminal velocity. What if? Here we see the graph of the computational model with drag with an initial downward velocity. Since the terminal velocity is dependent upon the drag force being equal in magnitude but opposite in direction to the force due to gravity, the terminal velocity would be the same. However, since the drag force is proportional to the velocity, we can reason that we will reach the terminal velocity faster if there's an initial downward velocity. Thank you.